Okay, so at this point, let's run the simulation, the setup, pretty much the same conditions as the 2D case. So remember, we have the mesh, drag and drop here, update, right click, update. So it will convert the mesh from the Ansys measure to Fluent format. So here you see that you start to have all the files. Okay, so while it's doing the conversion, let me just go. So I'm saving everything here in my desktop. And see here that you have Gen1, Sys1, okay, where you are saving all files. So as I go back here, so for instance, you go here, properties. See here, Sys1, you are saving the mesh. So in Sys1, you have the mesh. So now when we have the Fluent case and we start to work in Fluent, we're going to see Flu1 and everything. So let's do it. So now I have this, and to launch Fluent, double click there. See here, directory name Flu1. Always remember, double precision. Okay. Choose the number of processors, 4 in my case. Actually I have 6, but let me put 4. Okay, and it will open. It will create this directory name with all the Fluent information. So as you go back here, probably I think, see that now you see Flu1, and you know that a specific case, you're going to have all the files there. So then it's going to start to write files there. So that's how you know where scenes are, okay? What I say that I don't like to launch Fluent within the Workbench because it starts to save backup files, a lot of information, and sometimes it's difficult to move in this directory hierarchy. So it's better to go outside of this Workbench bubble. So most of the time, just use Workbench to generate geometry mesh and convert it. That's all. Okay, so we're here. Okay, so we have the mesh, everything here, your reference system, and those arrows there. So for instance, let me show something that I haven't shown so far, but let me show it here right now. So see these options here, domain. See here that you have a scale. This is very important. Okay, so you open this, it's going to give you the dimensions of your domain. So always check this one, because sometimes it might happen that it's doing the wrong conversions, you forget to do something, or you put a different conversion, you have the wrong dimensions. Okay, so you check here that you have the right dimensions. In this case, from 0 to 7 it's okay, but if they are not right, you can scale everything. Okay, so you can convert units or use scaling factors to put it there. It's up to you. The other thing that I wanted to show you is here, so this starts to become important in 3D, mesh quality. So you press here, quality, evaluate mesh, and this will give you a diagnostic of the mesh quality. Okay, so see that you have this value here. This is the one that you should control. Okay, so this value shouldn't be lower than 10 to the minus 2. It can be, but a very good mesh, a mesh that is not going to give you problems, it's when this value is larger than 10 to the minus 2 or 0.01. Okay, so you have it lower than that, you can run, but you know that you might have some numerical issues, a little bit diffusion. But always check this. And here also you have another option in quality, improve mesh quality. So in the case that you see that this mesh quality is not very good, you go here, improve mesh quality, and then you press improve, and it will do some smoothing of the mesh, and it will try to improve to get a better mesh. Okay, so then you create evaluate and see that the values, see here the 0.16, which is already good one. Now it went to 0.3, which is even better. Okay, so it's doing some smoothing to improve the mesh quality. But use this one only if you have values lower than 0.01. Okay, and also, by the way, not necessarily when you improve mesh quality means that it's going to get a better mesh. Sometimes it cannot do anything, so there is no point. Okay, but most of the time it will work. So these are options that I show you now here in 3D where they are useful. In 2D, most of the time you're going to get good quality meshes, small meshes, and the good scaling, so there is no need to check that one, but it's one you can check. And also here you go in info size. See here that you have the mesh size. Okay, so you have memory size, a few options. So now let's set up the case. We have done everything, so let's follow the vertical workflow here. So we go here, setup, general. This is, we have said that this is okay. We have a steady, pressure based, no gravity for the moment. This is okay. Then models. Here's where you choose your models. For the moment, we're only interested here. So when we go later now in the course and we start to see more lectures, we're going to see all these constants, everything different models. But the K omega SST, I have to say that is the most general one. Okay, it will give you good result most of the time. I say most of the time because it has deficiencies that we're going to explore later. But the fact that it has deficiencies doesn't mean that it's not a good model. It's okay, but you should be aware of that. Then go in materials, define materials properties. So again, we say this one like this, and this one should be 106 to give a Reynolds of 100,000 using an inlet velocity of 1. So here, then here, nothing to do there. Boundary conditions, double click there and see inlet, velocity inlet. And let's put the velocity inlet 1 and normal to boundary. And here it's up to you. So now in this case, let me use 1 and 2 there. Okay, different from the previous 2D case. So let me put that, there is no problem. Apply. Then wall is a wall. See that there is no symmetry. Pressure outlet. It's okay, you fix it at 0 at the outlet, and here let's put 1 and 2. And we're done with boundary conditions. Nothing to do here, nothing to do here. These are advanced options. Reference values, remember this is to compute coefficients. Usually we use the mean values at the inlet, so if you select there, it will put those values, but you can choose, you can put manually any value there that you want. Okay, it's up to you. Nothing to do here, nothing to do here. Okay, so at this point, we're pretty much doing well. So now we go to the solution, set up the solution method. So let me remember every now and then, save everything. Sometimes mysteriously crash. By the way, you can also run without using the GUI, okay? There is more advanced options, but because this GUI, when you start to become a power user, you will see that this GUI is not necessarily anymore. No, it's not necessary anymore. So here you have the method. So you have different methods. So what is Fluent proposing by default, I think you can take it, it's a good one. But this case in 3D is interesting. Okay, so see here that you have different methods. So you can run, and I invite you to run with the couple and then run using the simple and check the cost per iteration. Okay, you will see that the simple, the cost for iteration is very low. That is, it's very fast. Each iteration is very fast. Instead, the couple is heavy. Each iteration takes time, but it might happen that the couple, it can reduce the residuals much faster than the simple. Okay, so I say it can reduce because that not necessarily means that the couple will have better convergence rate or better convergence. Okay, but you can test between both of them and you will see. Without doubt, the couple will consume more memory. So as you go here and you launch the task manager, as you monitor the memory, you will see that this couple, by the way, look at that, I'm already using like 16 gigs of memory for this case. It's not the actual mesh, but this mesh will be using probably 2 or 3 gigs of memory. So you monitor your memory, okay? Because large meshes in the coupled solver use a lot of memory. But for the time being, let's use this. Then you move to control. This is related to the solution method. Okay, later we're going to talk about this on the relaxation, but use default values. Report monitors, as usual, define the monitor. So we know that we want to create the flux report for the mass flow. So inlet, outlet, I will call it imbalance. You can leave the default name, it's up to you. Report to plot, okay. And then I want to also create the one for the y plus in the surface. Okay, so I want a facet average. I select the wall, the quantities here, turbulence, and then you have y plus, you call it y plus average. You can save it to a plot. Also, you can save the file. It's up to you. So in this case, just to the plot there. And if you want to create more monitors, it's up to you. So you can create like maximum truncated energy, whatever. Okay, it's up to you. These two, for these cases, are fine. Monitors, residuals, default residuals are okay. Nothing else to do here. So register, this is advanced initialization, and now we can initialize. Okay, so you can use a standard initialization using inlet free stream values like this, or the hybrid initialization. Okay, so in this case I will use this one, that usually this one, it can give you much better results than the standard one, or the one that you have uniform values. So this one might give you better results, better values, so you can get faster convergence, but not necessarily is the case, just to show you. Calculation activities. So here you can save. This is important because you can say you can put here the saving frequency. So far we have run and up to the latest iteration, but sometimes you don't run 100 or 200 iterations. That is fast. Sometimes you run 10,000 iterations. So it's a good idea to save with a given frequency. This is where you give that frequency. So let's say that I want to save every 100 iterations. You would save. So this is important because it might happen that the solution crash. I know you have a power failure, your computer switch off. So you know that when you reach 100, you save the solution, and then you have a problem, then you can restart from that. Okay, you need to restart from 0. And as you go to edit here, you have some other options, and you have this one. So if you don't put anything, it will save the solution every 100 iterations. So if you are running up to 10,000, you will have 100 files, okay? But it might be the case that you don't need to have those 100 files. So you say here, retain the most recent files. So it's retaining the last 5 files. So in that case, if you're running to 10,000, it's just getting the last 5 files. Okay, so it will be from 10,000 the 5 last files. Okay, so usually this is a good idea. I put here 5. Sometimes I put 2 if I have very large files. Okay, but usually if you are not interested in keeping all those files with the saving frequency, just leave this option. That most of the time for steady flows, this is recommended. This is that standard workflow approach that you follow. Here, this is also, you can add some stuff, but for the moment, this is advanced option. We need to touch everything again and invite you to press this button help, and you can get the help and see what is going on there. So at this point, we're ready to run again every now and then and save project, and we can run. Okay, so let me change here. Okay, saving everything. So if I go here, see the file. So in the Fluent case, if I go here, see that now I have many files. So see that you have your mesh and case setup, initial solution. This is the settings if you want to copy settings to somewhere else. So you start to get all the files. So I want to run to 1,000, and let me press calculate. And at this point, let's wait. Okay, so this will be a little bit slow. Now we're almost 500,000 cells in my case, and running with 4 cores. Be careful, monitor also your memory, but I have to say that most of the modern laptops today have at least 8 gigs of memory, which I think it is more than enough to run this. So see that I have a rather powerful laptop. I have 32 gigs of memory, 6 cores. Okay, so for me it's not a problem, but maybe monitor this one. If for you memory is a problem, reduce the cell count, but I'm sure that if you have 8 gigs, it's not a problem. So see that here we have y plus value. So see that this is for this y plus value, we see that it's a wall modeling. We're using wall functions. We have here the imbalance. Okay, so this is the mass flow at the inlet minus the mass flow at the outlet. So the method is conservative, so this imbalance should be close to 0. Or in other words, what is going on in is going out. And your residuals. Okay, so everything monitoring here, and everything seems to be smooth here. Okay, and let's wait a little bit here. So this might take a long time to run. Or long time doesn't mean days, but probably 10-20 minutes. So let's wait a little bit and see you later. Okay, in my case, I arrived at a converge solution. So let's see what we have. Press OK here. So look at my residuals have a nice convergence rate, but not necessarily means that you are reaching 10 to the minus 3, that you have reached a converge solution. So remember that is why it's important to monitor some other quantities. So as we look at the imbalance, see that it's kind of steady, it's not oscillating much, it's a low value. And Y plus also, maybe we might need to run a little bit longer in this case. So see that Y plus is a direct indication of wall shear stresses, okay? So see that this one is still it's not straight here, maybe still it is oscillating, it still is converging. So it might be a good idea to let it run for a little bit longer until you see that this one becomes straight or you have a statistically steady trend here, okay? In this case, I'm not going to run it anymore, it's up to you, but see that these are things that you need to monitor. In the case that, let's say, starting aerodynamics, you are computing forces, you're going to monitor the forces, and you see that if those forces still are oscillating, you need to run longer those simulations, okay? In this case, I will take it for granted, it's a good one, but it might this might need it's an indication that you might need to run it a little bit longer. So we have a solution, and what we need to do now is just the post-processing, okay? So you have everything, and now you go here, graphics, contours, and then at the wall, remember that we can plot the Y plus value. You have it here. So here you have the distribution, okay? So if I will recall, this will be this is the inlet, and then you have the outlet, okay? So you have your distribution there. You can check the pressure also. So inlet, outlet, so this is the inlet and the outlet. So, and then also you can plot velocity. Velocity, remember the wall will be 0, okay? But if you switch off this option, you're plotting the now next, in this cell next to that. So here you can get an idea of the entrance length. That is something that you can compute also, the entrance length as we flow now, how long it takes to develop the fully turbulent flow. So now as you go here to surfaces, so remember previously we created lines. Here we can create, let's say, a plane. So see that here is asking you the reference, so you can choose like this or like this. I will choose this one, and it will put it in the middle set. I know that is the middle point that is dissecting my domain, and you create that surface, okay? So see here that you have it there. As you go here, you can plot there. So now I hide that one, and see that now you can do your plotting in this plane, and here you have the velocity. So you have your velocity there. Okay, so also you can add the line plot. So you can go here and new line, and it's the same stuff as previously. I will do the plotting here, 6, 9, and then I will go here. I know I don't recall, so probably minus 0, 1, 0, 1, 0, 0 is okay. So I created a line there, and let's see if I see it here. So I have it there. Okay, so but in this case, so see, this is the importance of knowing your reference system, that how you are orienting things. So see that one, I put it here at the beginning where this is the inlet. I need to put it in the other extreme. So if I go back here, it should be 0, 1. 0, 0, 1. So close. So let me go here. So see, this is important how you put your reference system. So now I have it at the outlet. So this is okay. We have these two lines. What else we can do? So later I'm going to show you to do more advanced post-processing, the Y plus, all that stuff here, but this is the basic sense that we can do. You have vectors. Be careful, do not put the vectors in the whole domain, because you're going to, it's likely it's going to crash because you have too much information on your screen. For instance, this can be helpful, pass lines. So let me show you how to use this one. So basically this is to release string lines from a surface. So let's say that I want to release the string lines from the inlet. So you press here and see that you have there your string lines. Okay, this is the flow path. Okay, so you can change here the integration constant, the steps that it will follow. Okay, so you can get longer string lines. So in this case, they are straight, but if you have, I don't know, some funky geometries with elbows, pipes, or thermodynamics, you will see that it will follow vortices and everything. It's quite nice to look at. So you can put the poles here, so see that here you can see how it's following those paths, how see that it's accelerating here. So this is cool. Now this is stuff nice things to visualize. Again, be careful, because if you have very large meshes and if you put all the strings lines, it's likely that it will crash. So always play around, put a large value there, and then start to adjust those large values. Vectors, it will be the same as I mentioned. So vectors, you are going to put it in the plane. Do not put it in the volume because it's likely will crash. So let me skip 2, and then you put it there and see that you have your vectors there. Nice vectors. Okay, particle tracks, for the moment we are not going to work with that. Then, for instance, plots. Remember, you have this XY plot, so we can plot in this line that we just created. See that we're plotting that quantity. So I would like to plot there. Okay, this. Okay, no. So leave it like this. Should be 1, 0, and I want to plot there. Okay, velocity. So this is my velocity profile. You can do the same for the turbulent quantities. So see that here you have the turbulent kinetic energy. Boom. Following that, you have the dissipation. Okay, so you go dissipation rate, and you have all your quantities there. So see here that as we're using wall functions, the quantity does not go to 0. No, it's dissipating everything in the wall. So as you check here, the y plus value, the average is something about 30. Okay, so that's why it doesn't go to 0. As you recall the 2D cases in the 2D, when you have the very, very, very fine mesh, it went somewhere close to 0 because you're already in the viscous layer, so there you don't dissipate anything. Anyways, and then as you move here, okay, you have these plops. The other interesting entry here is reports. Okay, reports, again, you can do a posteriori all these reports definitions. So for instance, you want to recompute fluxes, you go here, fluxes, and just compute it here. So see inlet, outlet. So you want to compute forces, you have it there. So you select the wall and you have here the forces. Then you also select the direction vector. You have moments, center of pressure. Okay, and also you have all these integrals available. So let me check the surface integral, the wall. So as you compute area, it will give you the surface area. Okay, and then you have facet, let's say the maximum, and I want to know the maximum y plus. Select, and you have there the maximum y plus. It's also possible to know the location. Those are more advanced stuff, but as you see, you can do a lot of post-processing here. So this is all for this case. I have to say the basis attack. So later, the next video, I'm going to show you how to do exactly the same stuff, but in Fluent, but it's exactly the same, the same steps, plus also how to save the solution. Also, we saw that how to save the solution along this line of, let's say, velocity, wall shear stresses, and then we're going to do the plotting of the y plus against u plus, okay, using an external program. Okay, so that will be the object of the next video. So at this point, okay, we can let me close here. Okay, so you select this one, it will save the setting files, and you can use that setting file to set up the new case. So I will do it. Okay, so it's saving everything. Okay, it's closed, and see that as you go back to your directory structure, this is the setting file. So in these setting files, you have exactly the same setup that we put. So in the next video that we're going to go outside this workbench, we just need to here to open this, and we need just to copy this, and probably we only need to copy this file. We only need the case file, okay? So just get the case file, put it somewhere else, and then you can run. So at this point, I think we're done, okay? So remember, we run this case. We didn't run this one because I put here a very large mesh, okay? But you can modify this one. If you want to run using this one, remember that you need to set up your name it selection for the boundary conditions, okay? So I think at this point, I'm done with this case. Thank you for the attention. See you next video. Bye.